Hello and a big welcome back to all my subscribers, and if you're not a subscriber, why not? I thought today I'd focus a bit on software. I am having some issues with the hardware on my M68K build, and so there's not really a lot of progress to be shown there. So I thought what I'd do is go back and try and show people this Toolchain that I'm using and what I'm using to develop software for this particular build. And what you can see on screen here is my make file for the project, and this one is just for the simple one that I use for debugging. There's another one which has a bootloader and all kinds of other stuff included, but this is just the bootloader, and I use this when I build my debugging one. Now, as you can see here, that what I've got is the Toolchain is basically a cross compiler, because I'm creating this on my Linux machine and then I'm cross compiling the code, the binary, to work on my Motorola 68K. So a cross compiler is a compiler that runs on one architecture, like my Linux machine, AMD, but it generates binaries for another one. So this M68K Linux GNU toolchain lets me compile programs for a M68K processor on a modern x86 system. So the advantages of cross compilers, obviously, they make working on a retro hardware feasible without actually requiring vintage development tools, and they let me simplify the integration, and I can do modern debugging and version control, etc. And you get precise control over output binaries for ROM and RAM and custom layouts and whatever. So in modern development, cross compilation is essential where the platform that you're compiling for on the target system is impractical. It's an especially useful in a project like this where retro hardware, like the M68K, is involved, and the target hardware doesn't have the resources, CPU power, memory, storage, etc., to run the full compiler yet. And the development environment is more efficient on a modern system because I get, an editor and a debugger and version control and all that sort of good stuff. So using the cross compiler lets me leverage the modern system but generate code for both the emulator actually and the real hardware. So it lets me debug binaries on a modern host before I can try and transfer them over to the hardware. So cross compilers are typically built with a specific tool chain, where you get the host architecture and then the target architecture. So in this example, the compiler runs on Linux, but its output binaries are M68K. And there's a binary application interface that specifies the calling convention, the data layouts, and ensures compatibility with the target system. So a toolchain like the M68K Linux GNU includes the assembler, the compiler, the linker, and binary utilities, like I'm using here, object copy. You also get things like strip and readelf for manipulating and analyzing the binaries. So the key is that each component is designed and specifically configured to understand the target architecture. So cross compilers let you write software that runs on both hardware and emulators, and that's important because for me, I was using this with the QEMU emulator to try and test the memory and the RAM and the ROM before I started using the actual hardware. And that's really helpful from a debugging purposes, because I can't actually get onto the hardware and do any debugging. And part of my frustration at the moment is I don't have enough debugging information that I can get, because I'm heavily reliant on the logic analyzer and a logic probe, which really isn't telling me a whole lot much of the time. So the M68K Linux GNU is part of the GNU bin utils suite. It can generate machine code for the Motorola 68K family of processor. It's a modern assembler. and it makes human readable assembly into machine readable object files. Typically it outputs an ELF executable and linkable format. ELF, which is an executable and linkable format. And it's sort of a standard in modern operating systems and with the GNU toolchain. So it supports the full M68K instruction set. It includes various addressing modes like direct, indirect, and immediate addressing. It allows directives like dot section, dot global, dot EQ, and others for controlling the layout of your assembly code. And it allows embedding of debugging information when you're using the -G flag. So when you're working with the toolchain, it's not standalone. You get all of the other stuff for assembly, linking, and binary manipulation. And you'll notice here I've got a custom linker script. Now, when you're cross-compiling, linker scripts are vital to define how the output binary is laid out, especially in an embedded project or where there's no default linker script. So you can place the code in the correct place, so the code is placed in ROM at the correct starting address. RAM sections are allocated for memory mapped IO regions are specified, etc. So the modern compilers come with a default linker script, so if you're not doing cross-compiling, or even if you are in some cases, there will be a default linker script, which is great for general purpose operating system. This is why you generally don't have to do it if you're writing a C program on a modern computer for a modern computer, because there's a default linker script in there for you already. But it'll set the entry points, the memory layout, segment addresses, and this controls read, write, execution, permissions. For example, the .text in assembly might map to the ROM region, .data to the RAM region, .bss, which is uninitialized variables, go to RAM but start zeroed. So all of that is done, or can be done with the linker script, like I've got here. So the first bit that you see outside of the comment is the memory region. And typically you put the memory region first. So this block defines the memory regions for the target system, my personal build, and each region specifies the location of the origin and the size, which is length. So here I'm defining the ROM size and length and where it starts. So it's starting at address 0 and it spans 4 megabytes. The RX means that it's readable and executable, but not writable. So if you look at RAM, which starts immediately after and spans 4 megabytes, the RW means it's readable and writable. And then we move into the GPIO addresses, and each of these is marked as read-write, and then they start 1 megabyte after the other. And there's additional memory mapped addresses I could put in here for my full length. And then the next bit you define is the sections. So the first section here is the text section, and that is basically your program, and that's going to get put into ROM in this example, and it's aligned on a 4-byte boundary, so that it's aligned properly for all the instructions. And this bit tells it to include all the .text sections from all the input files, and the wildcard matches any file. And then this into ROM places it in the previously defined memory section up here. Now the next one is the data, and data will go into RAM, and basically it's the same thing. It's aligned on 4-byte boundaries, and marks the starting address of the data section, includes everything that is data, and then this marks the end of the data section, and that's put into ROM. Actually, I should go into RAM. And then the next bit is your stack out, the BSS, which is the uninitialized variables, and then you have the allocated stack, which goes into RAM, starts at the top of the RAM. So this is the basics of the tool set. But one thing I did want to it was actually ROM, sorry. One thing I did want to show you was how I'm splitting the binary. Let me just go and fix this first. Right, you'll notice here that I'm running these commands which split the binary into high and low. If we look at it, there is the binary.bin which gets created, and then that gets split alternate high and low. So if we do, I don't know how much of this it'll show. Okay, it's not so much. And then we look at low, and then we look at high. You can see here what's happening is that it takes these bytes, puts it into the low one, then it takes this higher one, puts it into the high, this goes into low, this goes into high, this goes into low, this goes into high, etc., etc., and it just repeats that pattern. But basically the idea here is to split it into the two ROM chips that I have marked high and low, which you'll often see on my videos. And I went through a huge number of different ways of doing this before I finally settled on XXD. I was using DD. I had done all sorts of things with grep and awk and things, but XXD and cut actually ended up being the best way to work this. In my other makefile, I have a similar sort of command, but for Windows, and I've got the Windows toolchain here. So when I was building this on Windows so that I could create this for the emulator, but yeah, I had to use a PowerShell command to get the encoding on Windows. Anyway, that's it for me today. I hope you enjoyed this. I apologize that I didn't have any update on the other one, on the physical build, but as I say, I'm running into hardware problems there, and so I just decided I'd quickly cover the tool chain. If you want more information about the tool chain or the cross compiler or the linker scripts or any of that sort of stuff, let me know in the comments and I'll try and expand on what I'm doing with all of that. Lovely. Okay, thank you very much for joining me today, and if you like this sort of things, like and share and subscribe and press the bell and do all that YouTube stuff, and I will see you later. Thanks a lot. Bye.